Okay, so good morning, everybody. As Megan announced, I will be talking about climate variability across Iowa and the science, quote unquote, science of seasonal predictability. I've been state climatologist almost 3 years, and as Megan mentioned, I work at the Iowa Department of Agriculture and Land Stewardship. So thank you for being with us today, and I appreciate the opportunity to present to you. So some presentation highlights. We'll talk about the Iowa Observation Network because this is the network in which we get weather observations, temperature, precipitation, and those records build a trend. Those records build a story for the state, where we've been, where we are, and where we're going. Then we'll talk a little about climate variability, and variability meaning how we vary through the year, through the decades, through the centuries, and then some trends that we're seeing going back to 1895, but also over the last 30 years. We'll talk a little bit about precipitation extremes, and then we'll look at some atmospheric oscillations. Now, I'll explain what an oscillation is, but it's basically periodic behavior in the larger scale atmosphere that impacts weather across the United States. Then we'll look at short-term and seasonal outlooks. Those are the products that we get knowing that a specific oscillation is present. Basically, if El Nino or La Nina is present, other types of shorter-term oscillations, the Arctic oscillations, which can give us Arctic air outbreaks that we've seen over the last few years. Then we'll look at current conditions and drought. We're in a drought, and especially in Western Iowa. And we'll also look at the outlooks that will suggest which way we're moving in terms of dryness and wetness. And then finally, we'll do summary and I'll have questions. Okay, so the first thing we'll look at is the Iowa Observation Network. It's composed of the National Weather Service co-op stations, which report daily at 7 a.m. typically, and then the CoCoRaHS Rain Gauge Network, which supplements rainfall data that we see across the state. So if we look at a map of the state of Iowa, where you see those red dots there, are those temperatures, in fact, those are the co-op stations across the state. There's a pretty good distribution around Iowa. Being a rural state, we do have gaps in that data. Now, as part of my responsibility as state climatologist, I work with the National Weather Service and other atmospheric scientists to interpolate data within those gaps in the observation network, so we get a more robust, a better temperature and precipitation, especially precipitation record, given that we're seeing more variability in where rain falls and the intensity and frequency in which rain falls, as well as snowfall. So to augment the precipitation network that we have across the state, we have the Community Collaborative Rain, Hail, and Snow Network, CoCoRaHS. This network has been around for 20 years. It was developed in Colorado. And what you can see on the map here are many of the CoCoRaHS reporting stations across the state. Now, again, this is a civilian network. You buy a standardized rain gauge that holds 11 inches of water, or you contact me and I'll send you one if you want to be a consistent observer. This data I use for FSA criterion, crop indemnity insurance, all kinds of issues. So if we have consistent records, National Weather Service and CoCoRaHS, this will build a more coherent and more robust temperature and precipitation trend that we then can feed into forecast and climate models to give us better products moving forward, especially climate outlooks. Now, in 2018, we had a D3 drought in southeastern Iowa, and I was able to give 6 to 10 drought meetings down in that neck of the woods in June, July, and August as the peak of drought was occurring, which was August 21st. Explaining to farmers and ag stakeholders that having better rain gauge data helps us in drought monitoring and also wetness monitoring really made an impact on the groups that I talked to. And we went from having one National Weather Service co-op station in the middle of those counties, Appanoose, Lucas, Van Buren counties, with a few CoCoRaHS gauges there. We went from a few to 45 to 50 new gauges down there because we did make a concerted effort to tell farmers and stakeholders that better precipitation information can only help us do our jobs better, especially when it comes to drought. And as you can see, that D3 region was pretty good overlap with where we saw all those new gauges. The colored dots there were the new gauges that we saw that year. Okay, so briefly, now I'll talk about weather and climate because we do see some confusion there, especially with atmospheric scientists. As scientists, we try to explain things in non-technical terms, but sometimes we fail. So weather and climate, let's talk about that. Weather is the day-to-day state of the atmosphere. So we think of short-term, seconds, thunderstorms, tornadoes, to minutes, out to, let's say, 2 weeks, 7 to 10 days is what we consider weather. We generally talk about weather. You know, everybody likes to talk about weather. What's the temperature? What's the relative humidity? How much water vapor is in the atmosphere? Is it going to snow this weekend? How much snow are we going to get? So when we talk about short-term variations in the atmosphere, that's weather. Now, on the other hand, climate is the weather averaged for a specific location over a period of time. And typically, as climatologists, we use the last full 30 years, 30-year decade, climate decade as we call it, gives us a good measure that we can use to compare and contrast weather events. For example, we talked about the derecho already, but we can use our climatology to say, how often do we expect a derecho across the state of Iowa? Typically every 2 years. If we go back to 1980, we've had 11 on record. This derecho, as I mentioned, will go down in state history as the strongest. 30-year climatology is a great baseline. It allows us to average various oscillations, which I'll talk about, various atmospheric behaviors, so we get a good baseline to compare weather events. I will mention that we're currently on the 1981 to 2010 climate decade, but this will be updated to the 1991-2020 climate decade in May when the new data is released. So we'll have more on that as we approach. Climate information includes statistical weather information, the typical high, the typical low, the average temperature, how much rainfall we would expect for a location on a given day or a given month or even a given year. And then we can compare and contrast the weather extremes that we see at a location. That's what we call climatology. So if we look at a basic plot of weather versus climatology, weather is that daily or weekly variation in temperature, precipitation, whereas you average those wiggles out, you get that green line. Green line is climatology. That's where I deal with. So that green line is the baseline for which we compare, oh, this temperature is 3 degrees above average. When have we seen temperatures like this? What type of weather patterns have we seen? What are the impacts that we'll see given the variability that we're seeing in the short term? Also, if we look at winter and summer, seasonally, we always expect the coldest temperatures in winter, warmest temperatures in summer. There is variability in all seasons, but if we average those out, temperature-wise, we typically are near average. I'll show this year's summary, but we're generally 1 to 2 degrees above or below what we would expect temperature-wise. Where we see greater variability, especially weekly, monthly to yearly, is in the precipitation field, and I'll talk about that as we move forward. And here we are. So let's talk about precipitation trends. We'll go historically. The federal record, the official record goes back to 1895. Then we'll look at the last 30 years and then kind of compare and contrast what we've seen in the long-term trends versus the short-term trends in precipitation and temperature. So if we look at the annual average temperature for the state of Iowa, since 1895, each of those dots is a year. The higher the peak, the warmer the year, the lower the trough, the colder the year. Now you can see spikes and troughs as we move forward through the late 1900s into the 20th century and then the 21st century. That blue is the trend. So we take all those years and we pull the trend out, and that gives us an idea if we're warming or cooling. What we've seen per decade since 1895 is a 1/10 of a degree increase in the atmospheric temperature. So we've seen a warming as we move through the decades. So we're about 1.3 degrees above average compared to where we were back in 1895. Now, by proxy, by a physical relationship we call the Clausius-Clapeyron equation, Any increase in temperature in the atmosphere necessitates an increase in the amount of water vapor that can be held in the atmosphere. So this is the precipitation annual averaged for the state of Iowa since 1895. Same plot as temperature. The higher the peak there, the wetter the year, the lower the trough there, the drier the year. The top peak here is 1993, the Great Flood year. Second wettest year on record was 2018. 2019 was the 12th wettest year on record. You take those 2 years together, wettest 2 calendar years going back 148 years. So we've been in a pretty wet stretch over the last several years. Decadally, if we look at the trend since 1895, we're a little over 0.4 of an inch increase per decade. So we're getting wetter. Now, what this betrays is that certain parts of the state are becoming wetter, while other parts of the state are not seeing as much precipitation as we have historically. Now, if we look at the same plots, but for the 30-year trend, so the last 30 years, what we see temperature-wise since 1990 is a doubling of the warming that we've seen in the atmosphere, so 0.2 of a degree over the last 30 years. And again, by proxy with the Clausius-Clapeyron equation, which again tells us how much water vapor can be held in the atmosphere, we've seen almost a little under doubling of that amount of precipitation per decade. So almost 0.7 of an inch increase per decade across the state of Iowa. The general average for the state varies where you are from the southeast corner to the northwest corner, but generally 32 to 38 inches, depending on where you are across the state, and around 36 inches for the statewide average. Now, if we look at projected precipitation change by season, moving out forward into the end of the 21st century, so the time scale here is 2071 to 2099. This tells us wherever you see greener colors, that's where we expect an increase in the amount of precipitation in that season. So we see in winter, spring, and fall, an increase in the amount of precipitation, rainfall, snowfall. And let's define precipitation as anything water that falls out of the sky, liquid equivalent. So we melt snow, sleet, hail, and then add that to our other liquid forms of precipitation. And that's what precipitation is. Where we do see a decrease in the amount of rainfall is in summertime. Now, if we look back over the last several years, about the second week of July, we get into a pattern in which the faucet shuts off and we really don't get measurable widespread rainfall across the state until about August or the middle of August. Now in 2020, that faucet turned off relatively on time, and it didn't turn back on across the state until September. We had the third driest August on record, and that only contributed to the drought that we were seeing in west central Iowa and then expanding into northwest Iowa. So overall, if we look at a summary of these trends, what we're seeing is both long-term trend going back to 1895, but also the 30-year trend. We're seeing an increase in temperature and precipitation. Now, we're also seeing higher intensity events increasing. So we talk about, typically a National Weather Service co-op station would see a 1 to 2 inch rainfall over 24 hours, once or twice a year, 99th percentile. So a very small probability of that event occurring. What we've seen over the last 30 years are the chances or the probabilities of seeing 3+ inch rainfall events over 24 hours, while relatively small, 0.01%, we've actually seen those triple. So over the last 30 years compared to the historical trend. What this has impacts on are, of course, agricultural runoff, soil loss, nitrate loss. So we talk about cover crops and no-till as tools that we can use given the trends showing us an increase in the amount of rainfall and higher intensity rainfall. Now, as I showed you in the climate modeling plots prior to this slide, we are seeing seasonal spring and fall rainfalls occurring more often, but earlier in the season. And this has implications on planting and field work and also harvest. And that's what we saw in 2018 and 2019. 2020, we actually had a great window weather-wise for harvest or for planting, middle of April into May. And then it just so happened we had a drought set in and then a derecho. But we have seen historically an increase in those rainfalls in autumn and fall, or autumn and spring. Now, right in the middle, as I showed you on that plot, we're seeing rainfall on the decline in summertime, right around when crop is maturing, hottest time of the year when livestock need relief. So that is of concern that we're seeing. Now, given the temperature rise that we've seen across the state, we've actually increased the growing window by 9 to 10 days, which does give us a buffer, given that we are seeing increasing rainfalls when we do want to get out in the field. So that's a silver lining here. Okay, so briefly, we'll go over the 2020 summary, kind of set us up for drought conditions, but also setting us up for the talk about climate variability and what we've seen and what are those patterns and behaviors that impact weather across the state of Iowa. So for the final climatological summary, the statewide temperature averaged 49.2 degrees, and this was 1 degree above average or normal. Those two words are interchangeable in climatology. And that ties 1908, 1928, 1944, 1977, and 2015 as the 33rd warmest year on record. Now, as I mentioned, we do see less variability in the average monthly to monthly temperature. So that's why we can tie a lot of years, because temperature doesn't vary that much. On the flip side of that, precipitation does. So statewide, we averaged about a little under 29 inches, and that's a little over 6 inches less than normal. And this was ranking us as the 36th driest year on record. Now, there were climate divisions, which I'll show you a plot later, in western Iowa. So northwest, west central, and southwest Iowa were the top 10 driest years on record. And that is reflected in the drought conditions that we see. A warmer year occurred last in 2017, and a drier year last occurred in 2012. So we have seen some impacts on comparisons, I should say, between the 2012 drought versus 2020 drought. It's a little difficult to do that comparison. It's more apples to oranges than you would expect, given the large scale setup that goes into droughts. So we do want to add a note of caution there when you do hear 2012 comparisons, but that can be a whole other presentation. And in fact, I gave a presentation last week with the DNR. We'll go through these pretty fast. This is a departure from normal plot. So the higher that red bar, the more above average temperature was in that month. The lower the blue bar, the colder. We didn't really see any kind of epic records beside October being the 6th coldest October on record and November being the 10th warmest. Now, what stands out in the precipitation plot, those pink bars, the lower those pink bars, the drier that month. You can see August, of course, stands out. More of those pink bars pointing down than blue bars pointing up. So February was the 13th driest. April was the 17th driest, and then August was the 3rd driest. So we did have a pretty dry stretch, especially June, July, and August. And that's where we continued to see drought take hold in western Iowa. I'll skip this, which this plot tells the tale. This is the annual departure precipitation for 2020. Wherever you see those orange, reds, those warmer colors, that's where we were below average precipitation wise. Wherever you see those cold colors, greens and blues, that's where we were above average. Northeastern Iowa, we see departures anywhere from generally 2 to 4 inches. Where you see that red coloring in west central Iowa, where the initial D3 extreme drought region was visible in July into August, anywhere from 12 to 16 inches below average. So very dry conditions. We started to see precipitation deficits stack up in the fall of 2019. The saving grace for us moving into the growing season is that we had a loaded subsoil profile. So that subsoil profile, anywhere from the 95th to 99th percentile, you think of a sponge. 95% of that sponge is soaked. So ample subsoil moisture getting into the growing season, which started to mask the precipitation deficits, again, that we started stacking up in fall. So as you can see, it's kind of an island of dryness within the Midwest, but we have seen drought conditions continue to expand, generally west and north in wetter conditions over southern Iowa over the last 3 months. As I mentioned, the climate divisions, this will give you the ranking going back to 1895. So wherever you see those brown colors, those are dry climate divisions. Wherever you see the green, those are wet. So if you look at Climate Division 1, which is Northwest, Climate Division 4, West Central, and Climate Division 7 in Southwestern Iowa, 9th, and 8th. So top 10 dry years that we've seen. So it's really does tell you that drought conditions are there, and drought conditions will persist unless we see a major shakeup in the large scale circulation. And we'll get into that when I talk about variability and oscillations. And here we are. So atmospheric oscillations. Now that phrase might be a little too technical, and it is technical, but we think of the way that the atmosphere works as a spring or a pendulum, and there's a periodicity in which that pendulum swings back and forth. Well, we can think of atmospheric oscillations as acting somewhat as a pendulum in the atmosphere, and that does give us some predictability when we look at our short-term forecast models, but also our longer-term climate and numerical models. So basically, what an oscillation is. We'll call it a semi-periodic behavior in the large-scale atmosphere. We treat the atmosphere as a fluid, and these periodic behaviors impact short-term weather patterns and also longer-term seasonal behavior. So the plot I have here on the right-hand side is an oscillation that everybody knows, El Niño. El Niño is associated with a larger scale multi-decadal oscillation known as the El Niño-Southern Oscillation, or ENSO. So typically in wintertime, when the El Niño signal is present, we expect warmer than average conditions generally across the state of Iowa. Knowing that we've had El Niños going back hundreds of years and that we have records of the occurrence of El Niño, this gives us an idea of how to tune our climate models so that they can give us better outlooks moving forward, since we know that that phase of ENSO is present. Now, we term the behavior affecting weather at a longer term spatial scale or far away as a teleconnection. So generally what we're saying is in the Pacific Basin, depending on where thunderstorms are occurring, that impacts the jet stream path across the United States. And that's where we can get into wet behavior or dry behavior. Again, that's the periodicity that I'm talking about. That gives us some guidance when we're looking at forecasting and outlooks. Now, there are many oscillations that impact weather across the United States. Again, the ENSO, El Niño-Southern Oscillation, we all have heard El Niño. We're currently in a moderate La Niña, which is the cold phase. And I'll talk a little bit about what we expect in terms of the storm track and jet stream across the United States in wintertime and then moving into spring, given that the La Niña phase is present. I mentioned that El Niño is part of the Southern Oscillation. Southern Oscillation is multi-decadal, so it's a long-term oscillation in ocean and temperature, and atmospheric temperature along with pressure. So if you think of a big wheel as ENSO, or the Southern Oscillation, El Niño and La Niña is a smaller wheel that rotates around that bigger wheel, typically a 2 to 7 year cycle. So knowing that we have a 2 to 7 year cycle gives us forecastability and predictability in the climate models if we know which phase is present, or we know a phase is starting to become more apparent in the tropical Pacific. There is another oscillation called the Madden-Julian Oscillation. And basically this is thunderstorm activity in the Pacific Basin. It comes in 8 phases. So if you think of El Niño as a person riding a stationary bike, El Niño is a specific part of the tropical Pacific impacting sea surface temperatures in a specific region. The Madden-Julian Oscillation actually phases across the Pacific Basin and can impact and interact with El Nino or La Nina. So when we have an interaction like that, that's where we start to lose predictability and forecastability in the climate models. And that's when we fall back on longer term trends and climatology. So there is a science to this. Arctic oscillation is a weekly, several week out oscillation that is a negative or positive phase. So for example, if we get into a negative phase of the Arctic oscillation, we see the polar jet actually dip into the Midwest. And when we see that dip in the Midwest, that's when we get those Arctic air outbreaks, or we get more active storm tracks. So we get waves and waves of snowfall across the state. This happened at the end of January 2019 when we had the Arctic intrusion. So the shorter term periodicity of the Arctic oscillation does throw a wrench in longer term forecastability. But when we do see the phase moving from positive to negative, that does give us some indication that there is an expectation of colder and perhaps more precipitation that will impact the state. And then we have larger oscillations that interact, the North American oscillation and the Pacific decadal oscillation. I won't get into those because it's less predictable than the El Nino and Arctic oscillation. So those are the two that I'll concentrate on today. El Niño-Southern oscillation, ENSO. El Nino and La Nina are the warm and cool phases of a recurrent climate pattern across the tropical Pacific. If you look at the top plot, that is the El Nino phase. So that's where we're seeing warmer sea surface temperatures coupling with the large scale atmosphere. When that happens, we start to see a shift in thunderstorm activity in the Pacific, and it shifts it more towards South America and the Baja Peninsula in California. When we see El Nino, it impacts where the jet stream is across the United States. And as I mentioned, it's basically a 2 to 7 year cycle. And each phase can trigger predictable disruptions as we have analog years of temperature, precipitation, and wind speed and direction across the Midwest and over Iowa. So given that we know that we're in a moderate La Nina, we have an idea of the type of behavior that we see both short term, so moving out through January, but also longer term, spring into summer. And I'll show you those outlooks as we get towards the end of the presentation. As I mentioned, given the phase of El Nino or La Nina will impact where thunderstorm activity is in the Pacific Basin. And via that teleconnection that I mentioned earlier, that impacts where the jet stream is moving across the North American continent, United States. That jet stream is as a fast-moving channel of air that forces the highs and lows that give us precipitation events across the United States. So where that jet stream is gives us an idea of where the cold air will be based, but also where we can expect more precipitation. So in the La Nina phase, what we see in wintertime is a dip in the jet stream. And with that dip, colder air from the Arctic is allowed to intrude into the upper Midwest, basically the Dakotas through Montana. Now, where we see wetter behavior is the Pacific Northwest, but also the Ohio Valley. And then you look south of that jet stream, it's kind of cut off from any moisture or any of those transient low pressure systems that would bring precipitation. So we see drier conditions in the desert Southwest. Now, Iowa just happens to be right on the interface of what we call equal chances of above, below, or near average conditions. If we look at analog years or years in which La Nina is present, going back 50 years, you'll see a wide spread, a wide amount of variability in that signal, especially precipitation-wise. But if we average all those analog years together, the plot that you see on the right generally is what we see behavior-wise in wintertime. Now, we are seeing in the outlooks of an increase in the probability of wetter conditions starting to spread out from the Ohio Valley into Iowa, and we'll talk about that as we get to those slides. The second oscillation that impacts us, especially in wintertime, is that Arctic oscillation. And this refers to the atmospheric circulation over the mid to high latitudes. So high latitudes, we think of the Arctic, and this is the Northern Hemisphere. Southern Hemisphere acts differently because Antarctica is a continent with an ice shelf built on top of it, more ocean in the Southern Hemisphere, less ocean in the Northern Hemisphere, so we get different behavior. But with the Arctic Oscillation, gives us a location of where the jet stream or the storm track will be. So if we look here on the leftmost plot of the Northern Hemisphere, this is the positive phase of the Arctic Oscillation. When we see a positive phase in the AO, basically the jet stream is trapped up north, all that cold air stays bottled up in the Arctic, and we get into a less active storm track across the United States. Now, on the flip side of that, the plot on the right is the negative phase of the Arctic Oscillation. And when we get into a negative phase, the polar vortex, or the gateway, or the gate that holds all that cold air into the Arctic, starts to destabilize, and we get wobbles in the jet stream. When you start to get wobbles in the jet stream, you start to form meanders or dips in the jet stream. When you have dips, that's when the storm track is forced south and we have colder air. So long story short, for Iowa, when we get into the negative phase of the Arctic Oscillation, typically we expect colder than average temperatures, but also a more active storm track with more snowfall events. Currently, we're transitioning from a slightly negative phase of the Arctic Oscillation. We've had a few Alberta Clipper systems, fast moving systems that have given us those little snowfalls that make the roads slippery. We're starting to transition from that slightly negative phase to a positive phase. So a less active storm track as we move through the end of January into February. And this will be reflected in some of those outlooks that I'll show you. The main points here that I want to make, and I could talk about oscillations and how they impact predictability and forecastability for hours. So I'll have my contact information at the end of this presentation, so please reach out if you have any questions. But the main points I want to make, temperature and pressure variations over different time periods. So short term, let's say days to weeks, and then long term, years to decades, impact weather patterns, the large scale weather patterns that we see across the United States. Knowing which mode or phase of an oscillation is in, so El Nino or La Nina, gives us a general idea and a better idea of what atmospheric behavior we can expect temperature-wise and also precipitation-wise. And we get this, we know this from experience because we've had analog years in which we've seen a phase of El Nino or La Nina. We have a great temperature and precipitation record. Satellite remote sensing tools have allowed us to better analyze the El Nino, La Nina region in the tropical Pacific. So when we do see a phase starting to form or transition from ENSO, from La Nina to El Nino or back and forth, we have a better idea of what the forecastability will be and the predictability for that season. Now, when we're in an ENSO neutral phase, so right in the middle of the warm and cold phase, we don't get a lot of forecastability. That's when we fall back on our longer term trends, but also the shorter term activity that we've seen in the jet stream, for example, or those low pressure systems that give us precipitation. So in ENSO neutral conditions, you'll notice in the outlooks, there's less probabilistic integrity there. Probabilistic integrity meaning the probabilities will not give us a high amount of guidance. So then we have to move back onto those shorter 8 to 10 and 6 to 10 and 8 to 14 day outlooks. But overall, if we do know the phase of the Arctic Oscillation or the larger scale oscillations, we can tune our numerical models to behave as they would given the formation of a specific phase. Now, meteorology and climatology is not a clear-cut science. A lot of forecasts were busts this year, and speaking with Megan and field scouting with Megan, we had a lot of 7-day precipitation forecasts in spring into summer that were near 80 to 90% shots of having measurable rainfall, especially in western Iowa. Well, those forecasts turned out to be busts, and they didn't pan out. So when we have dry conditions at the surface, moving into spring and summer, knowing that a majority of the rainfall that we get is thunderstorm driven. If you don't have available subsoil moisture or subsurface moisture for those thunderstorms to feed on, they're not going to form. And sometimes the numerical models don't catch that. So having better rainfall information, having better soil moisture information to input to these climate models will give us more guidance, better, more robust guidance moving forward. So that's why COCORAS is such an important network for me and for the state in general. And as I mentioned, you can have interactions with the Madden-Julian oscillation. So you have thunderstorms set up in a specific part of the basin in the Pacific, and then El Nino is sitting there as well. When you have multiple oscillations behaving in unison, it's difficult for those longer-term climate models to pick out specific forecasts. So that's where we have predictability breaking down. Now, given that we model the atmosphere as a fluid, the forecast models do a pretty good job of getting the large scale behavior. It's getting those micro to mesoscale, so statewide level types of events that are hard. Case in point, the derecho. The derecho was not forecasted for the state of Iowa. Specific conditions need to be met for a derecho to form. Those were not present on the morning of August 10th. Not until that line moved across Nebraska did it hit an explosive atmosphere, generally east of Carroll, and then it intensified rapidly. So we do miss those extreme events. And extreme events are hard to model. But again, that's a topic for another discussion. I'll kind of piece this together. We have the Iowa Observation Network that gives us our trends. Those trends give us guidance as to what the atmosphere is behaving like on the longer term. And then we use that data to input into our climate models, our numerical forecast models, in unison with the oscillations that are present. So the phase of El Nino or La Nina. When you have all those things come together within a numerical model that are generally run on supercomputers, we output a forecast, the 7-day forecast, which gives us highs and lows in precipitation. We get into outlooks. The outlooks are actually kind of beyond that forecast window. So they give us a probabilistic idea of behavior and temperature and precipitation. So if we look at the NOAA, National Weather Service climatological outlooks, again, they're based on probabilities. Whereas the forecast that you see on the news in the morning or at night, those give us an idea of how much above average the temperature is. It can be 5 or 6 degrees above average. We'll be in the 40s today. That's, depending on where you are, 10 to 20 degrees above average. So that's what a forecast is. When we look at outlooks, we're dealing with probabilities or the chance that the behavior will be above or below normal. So wetter or drier, warmer and colder than the average. And that average, again, is that 30-year 1981 to 2010 baseline. As I sort of alluded to, it incorporates various pieces of science. So our numerical forecast models, the models that you see on TV. Now there's that joke that the GFS, the American model versus the European model are always diverging. So which model do you choose? I like to think about those spaghetti plots for hurricanes. You run those models multiple times with different parameterizations, and you get the track of that or the path of the hurricane impacting the Gulf Coast, for example. You get multiple plots. So we average those out. We use the ensemble or the average of all those spaghetti plots to kind of give us an idea of the track of the tropical system. We also, again, take in oceanic effects. So the phase of ENSO, Madden-Julian oscillation, sea surface temperatures, and how they're impacting the atmosphere. Are we seeing more thunderstorms in the Eastern Pacific Basin or the Western Pacific Basin? And the reason why we think about the Pacific Basin is because mid-latitude flow into the United States is west to east. So we're impacted, our air masses are modified over the Pacific, and that's what the general flow is. So that's why we put a lot of emphasis on Pacific oscillations. And then finally, recent trends in climatology. When we are in an ENSO neutral phase, for example, those recent trends in climatology give us better guidance as opposed to if we were in a phase. So we generally we use the color coding on these CPC Climate Prediction Center outlooks to tell us what we can expect temperature and precipitation wise. Above average behavior is typically above 33%, below is typically below 33%, and near normal is right in the middle, 33% to 30%, and then 30% to 25%. So right in that middle of the distribution. Now we can get into a probability here, which is called EC. EC is equal chance. That's where we're not getting a clear signal from the climate models that produce the outlooks. So with that EC, a lot of people say it's the climatological flip of the coin. We're just not getting robust guidance. So as I tell our stakeholders, and we'll get into these figures, let me orient you first with the probabilistic plots, and then we'll talk about them. On the left-hand side here is the temperature. On the right hand is precipitation. Wherever you see those warmer colors on the temperature plot, that's where we see higher probabilities. And those higher probabilities tell us that where that A, or that above average bullseye of 50%, there's a 50% probability over Texas into Oklahoma of above average temperatures, so warmer than average temperatures. Now, it's not a forecast, so it's not telling us how much above average we will be. It's just giving us guidance that we are a high probability of being above average. On the flip side, where you see those blue colors, that's where we have below average probabilities. So we have the expectation of colder than average temperatures. And this is the 8 to 14 day outlook. There's a 6 to 10 day outlook, and both of these outlooks are issued in the afternoon every day. What I tell our stakeholders and what I tell our general audiences is take these with as a snapshot in time. What I look at is how the trends evolve on a day-to-day basis. If we continue to see those warmer colors over the state of Iowa, those indicate that we're getting into a warmer than average atmosphere. So something's happening in the atmosphere that's producing probabilities of warmer than normal temperatures. When we get into spring and summer, on the right-hand side here, you'll notice that the green colors indicate higher probabilities of wetter than normal conditions. In spring and summer, typically when we see those elevated probabilities of warmer than average temperatures, those are tightly coupled with drier than average conditions. So those are some other trends that we look at, and that can give us some guidance as we move out into the longer term. So the second product that we use is the 3 to 4 week outlook. And this puts us into the middle of February. What we're seeing here is that classic La Nina signature that I mentioned earlier, where you have elevated probabilities of wetter conditions from the Ohio Valley and then stretching through the Pacific Northwest. Temperature-wise, we're in that EC category, or equal chance. We're not getting a really clear signal of whether we'll be above or below average. So when we do see that EC, we trend back to climatology. So there's a 34% chance when you see EC there that we'll see behavior that is normal for this time of year. Then we have the seasonal, or the monthly outlooks that are issued twice. The February outlook, this is the initial half-month lead, so it was issued this morning, in fact. Again, same probabilistic features as you saw in the short term, but what we're seeing for Iowa and much of the eastern 2/3 of the United States is an elevated signal for warmer than average conditions in February. Now, I mentioned that bullseye of above average precipitation behavior for the La Nina signal is starting to expand from the Ohio Valley further west. So now we do see an elevated signal for wetter than normal conditions in February. Now, December, January, February are the driest 3 months for the state of Iowa, with January being the driest month. So it doesn't take a lot to get above average, and it doesn't take a lot to be below average. But as we move into the growing season and you start to see those elevated probabilities increase across the state, those do give us some indication that we could start to get into a wetter pattern, especially March, April, May. So if we look at the secondary or the third product that we look at from the Climate Prediction Center, those are those seasonal time slices. So this is the 2.5 month lead, meaning that we're still 2.5 months out from this season, March, April, May. What we are seeing though is that La Nina signal in the Ohio Valley and then Pacific Northwest. Similar temperature behavior, a slightly increase in the probability of warmer temperatures getting into March, April, May. If we look at the April, May, June version of this, we're actually seeing that increase in the probability of wetter conditions across the state of Iowa. So given the drought conditions that we're seeing in western Iowa, this would be a welcome signal. Finally, if La Nina is still present end of spring into summertime, if we look at analog years in which the La Nina phase is still present, we do see where you see those brown colors, chances of drier than average conditions. Now there is a better than 50% probability of us transitioning into ENSO neutral conditions. So this will impact the dryness or wetness across the state. So more on this to come as we move into spring. Okay, so looking at the suite of outlooks that we have the short-term outlooks that go 6 to 10, 8 to 14 day, all the way out to seasonal. And these outlooks are available through 2022. Now, of course, we've been talking about predictability. That predictability tails off the further you get out into a season or a year. So I would take those longer-term forecast or longer-term outlooks with a grain of salt. Now, if we look at the outlook summary in general, the La Nina signal appears to continue through spring of 2021 with a slight probability of ENSO neutral conditions transitioning as we get into summertime. Now, talking about La Nina, we do have a wider spread of variability in wintertime. And what that means is if you look at the last 50 years in which, in years that have had a La Nina signal, where I showed the average precipitation, so over the Ohio Valley and then up into the Pacific Northwest, that's the average. But if you look at each individual component that goes into the average, the precipitation behavior is all over the place. So we don't take a lot of stock in the La Nina signal in terms of wintertime precipitation. And as you see in the outlooks as we go March, April, May, and April, May, June, that probability actually expands east, west, north, and south. So we are seeing at least some semblance in the forecast and outlook models that wetter than normal conditions are probable, or there's an elevated probability for those happening. Again, that's that dominant behavior that we see in the Ohio Valley that's starting to spill into the Midwest. Analog years, again, of La Nina, getting into spring and summer show warmer and drier chances. Now, where the silver lining is there, I mentioned the transition from ENSO neutral, or transition from La Nina to ENSO neutral, a higher probability, I believe 55%. So stay tuned with that. We're still 2.5 months out. A lot can happen in the large scale atmosphere. You think about the bomb cyclone event that we had in March of 2019. That was the fingerprints of the Arctic intrusion that happened at the end of January, I feel strongly impacted the circulation and led to that behavior in March. So short-term jostles to the large-scale atmosphere can impact those outlooks. So again, stay tuned for that. Now we'll look at current drought conditions, since drought is on the forefront of a lot of our farmer and ag stakeholders' minds, given the dryness that we saw in 2020, especially in western Iowa. If we look at the January 1st through December 31st, 2020, if we look at the 2020 yearly precipitation deficits for the state of Iowa, anywhere where you see those warm colors, that's where we're below average or drier than normal. Only in northeastern Iowa, do we see above average precipitation on the order of 4 to 6 inches. Now you look at extreme eastern Pottawatomie County getting into Cass and then Audubon counties, that's where we see precipitation deficits approaching 18 inches. The fingerprints of this drought go back into the fall of 2019. Even given the wet conditions, we had ample subsoil moisture that was hiding or masking these precipitation deficits. It wasn't until about mid-May into mid-June when we started seeing low relative humidity, high temperature, windy days that we really started diminishing subsoil and topsoil moisture, let alone the physiological processes of the row crops using subsoil moisture. So that's when drought really took hold and started expanding, especially in west central Iowa in July and August, and then expanding into northwestern Iowa into fall. This is the current U.S. Drought Monitor depiction. Now I'll kind of orient you to what this depiction, how it's created, I should say. So the drought depiction is released Thursday morning at 7 a.m. Eastern time, and it's backdated to Tuesday. So Tuesday at 7 a.m. Eastern time is when data cutoff occurs. So any rain or any precipitation that falls after that will not impact the drought depiction. It will impact the drought depiction next week. What we can see here is generally status quo. We haven't seen a lot of change over the last several weeks, and that's a function of winter time. Not a lot of precipitation, but also the driest part of the year. Now, if we were in summertime and seeing similar behavior, that's when we would see degradation in the drought depiction. I anticipate the depiction will remain status quo as we move through winter time. And then as we start to get into the wetter seasons, that's where we will see either improvement if we get into a wetter than normal circulation, or the flip side of that. Here is the U.S. Drought Monitor class change. This is a 3-month class change. What this tells you is if you're green or darker green, that's where we've seen improvement. That's where we've seen precipitation events falling across the state. Where you see yellow, that's where we've seen some degradation. This is basically the D0 or abnormally dry category, which abnormally dry is not drought, but it's giving us an indication that we're starting to dry out. And this is a part of the state, or parts of the state, that we do need to have more monitoring so we get better information to the drought monitor author. If we look at the 0 to 200 centimeter soil moisture percentile, this is about 80 inches. Wherever you see red on there, and this is a percentile plot, so again, using the sponge analogy, the redder the reds there, that's how much more available capacity is in the sponge. So if you look at the northwestern 2/3 of Iowa, we're at about a 20th percentile and below. So 80% capacity within that subsoil. We are dry. You can see that band of dryness, though, stretch from western Kansas all the way up into the northeastern states. I mentioned that the storm track has been further south, a higher intensity tropical season. So we have seen wetter than normal conditions, but the storm track has been locked there. That's where you see that band is effectively acting as a fence, and that's where we're not getting a lot of moisture presently. If we look at the anomaly plot, we call this the delta plot from the end of December. This tells us if we're increasing subsoil moisture or decreasing. You see in northwestern Iowa that light green percent, 10%. We've seen a 10% increase in the amount of subsoil moisture. And this is a model product, so it can't be taken as pure truth. But this does give us an indication that we have seen wider spread precipitation events. Now, when this precipitation fell, soil moisture or soil temperatures were still near freezing, slightly below and slightly above, depending on where we were in January. We did get a little bit of infiltration, especially in that top 4 inches, but pretty much not anywhere deeper, because we didn't have enough moisture to get that deep. And then we have to get into shallow frost as well. I want to I mentioned the 2012 drought and comparing it to 2020, because we do get concerns from farmers that we're seeing similar behavior back then. Are we seeing that behavior now? And can 2020 be as bad as 2012? Well, of course it could be, but I mentioned it's not an apples to apples comparison. If we look at 2012 with 140 years of records ahead of 2012, we had a wet stretch of years: 2007, sixth wettest; 2008, fifth wettest; 2009, 12th wettest; 2010, second wettest. So a very wet stretch of years getting into 2012. We had a cool and wet spring in 2011. So Iowa's aquifers were at or near historically high levels, and soil moisture reserves were near capacity as drought formed. A common question, as I mentioned, how does this drought compare to previous droughts? Well, there are a multitude of factors that need to be present to create drought conditions. Above average temperatures, moisture deficits, subsoil moisture, stream flow, precipitation deficits that drives all of those subsoil and surface moisture deficits. Also, time of year, location, soil type, any number of factors go into drought. Seasonal drought versus flash drought, which can form over weeks. So it's always difficult to place a current drought in historical perspective. At the time, 2012 was compared to 1988. 1988 drought began with a very dry spring. 2012 drought had its underpinnings in a very dry second half of 2011. So lots of things working there to create drought. So I would be cognizant of those 2012 versus 2020 drought comparisons if you hear those out in social media. Again, stick with the outlooks, stick with the soil moisture deficits, precipitation deficits. Those will tell the tale in terms of the possibility of this drought getting worse or getting better. Just to look at some plots from 2012 and 2011. This was for the year 2011. This is the annual precipitation. The warmer those colors, the more below average precipitation. So central Iowa, west central Iowa, 8 to 16 inches below average. We're seeing similar behavior across western Iowa in our precipitation deficits in 2020. But you get into 2012, dryness exploded across the Midwest, getting into the southern states as well. Precipitation deficits, widespread precipitation deficits above 6 inches, getting up towards the 20-inch mark. So having the previous question about drought formation in a specific part of the United States and impacts on Iowa, that's an apples to orange comparison as well. So I would steer clear of those direct comparisons because they're not always as fulsome as they should be and provide more stress than necessary. But the story here is you had widespread 2 years of precipitation deficit stacking up, leading to a drought that started in late 2011 that expanded into late 2013. So we're not there yet, but we're monitoring it. Finally, if we look at the seasonal drought outlook, this is issued by the Climate Prediction Center, and this was issued on December 17th, going through March 31st. We see drought persists, but we don't see any degradation, at least in this current product. Now, if we persistently stay dry getting into March, April, May, then we could see in future iterations of this drought development becoming likelier. But again, we'll have to wait to see how winter pans out. Expected precipitation, we're going into springtime dry, western Iowa especially dry, eastern Iowa not too bad right now. The 30-year climatological expectation for precipitation from April to July is anywhere from 14 to 20 inches, basically in that 16 to 18 inch threshold. Row crops require around 25 inches of water. Thanks, Megan, for that fact. We are seeing deficits of soil moisture in existence. They have been there for months. We can get into the what if game. What if we don't get the climatological expectation of precipitation? We're going to have dry subsoil. we're going to have continuing dry subsoil. What if we get into an active pattern? Well, we'll replenish that subsoil moisture. The point of this is we have an expectation of what to expect. Don't play the what ifs game, because it's will pan out. The best thing that we can do, get the most robust guidance, precipitation from expanded rain gauges to the drought monitor, so we have a better idea of the conditions that we're currently in and moving into the growing season. So if we look at the drought summary, 2020 started with ample subsoil moisture from a wet stretch of years. 2018, second wettest year on record. 2019, 12th wettest year on record. Put those 2 years together, the wettest 2 calendar years in 149 years of records. So this setup was much like we saw in 2012. Drought conditions, if we look forward, are likely to remain unchanged into early spring, given the quiet conditions in the driest season for the state of Iowa. Soil profiles into western Iowa, of course, are worsening when compared to eastern Iowa, where we have seen more timely and widespread precipitation events. So that west central northwestern corridor is the driest part of the state, and the spot that we really need to monitor with increased diligence in our monitoring of soil moisture and precipitation in western Iowa. And then finally, one of the main points that I'd like to make is comparing droughts against each other and amongst the historical record of droughts is not a clear-cut proposition. So when you do see those comparisons out there, be careful and cognizant of what those impacts are, what they're trying what story they're trying to tell. So the summary from the main points, which I probably did in the summary, drought and abnormally dry conditions unlikely to improve or degrade. So that's where we get that status quo or drought persisting. If we do get precipitation events or we do get into an active pattern, soils are likely to freeze as we get into the teeth of wintertime, so we won't have any infiltration. But having snowpack on top of that soil will give us an idea and will give us higher probabilities of getting at least some infiltration when the snowpack starts to melt. We typically abide by what we call the 40-20 rule. We would like highs in the 40s, lows in the 20s, so we get a gentle refreeze thaw cycle. So you're not running all that water off in one fell swoop, but you're also getting infiltration, starting at the top and then gently getting it down into the subsoil profile. Once you start to loosen up that soil and get moisture in there, it makes infiltration that much easier. La Nina looks to persist longer into spring with the possibility of a transition to ENSO neutral conditions. If that La Nina signal does persist into summertime, looking at historical years in which La Nina was present, modeling is hinting at persistence of dryness. So we could continue to be dry getting into the growing season. Finally, here's the Climatology Bureau's website. There's the link at the bottom. Google Iowa Climatology Bureau. It has historical reports, recent climatological maps, current conditions, all those outlooks, the drought monitor, anything that you would ever need to support decision making, short term, but also longer term, given those outlooks. And here's my contact information. I love talking to farmers. I love talking to stakeholders. I love talking to the general public. So please shoot me an email or shoot me an email or give me a call